Our last section is section 4. In a lot of ways we've covered this, but we're just going to go a little bit more in depth on a lot of these everyday forces that we've been talking about. So our goals today is we're going to look at the difference between mass and weight. We're going to take a closer look at normal forces and look how we find their direction and magnitude. We're going to describe air resistance because it turns out it is friction. And we're going to look at the difference between static and kinetic friction. So first we're going to talk about weight versus mass. So mass is the amount of matter in an object, okay? How much matter it has. We always measure mass in kilograms or grams. So if you just look at these two boxes and we wanted to know how much is really the key word there. If you're asking a question where it's how much of this do you have, that is kilograms or grams. So we might have these two boxes, and this small box might have a mass of 1 kilogram, and this box might have a mass of 10 kilograms, and it's just telling us how much matter we have. Weight is slightly different because weight is the force of gravity acting on the object. You can use Newton's second law to calculate weight using mass and acceleration due to gravity. So if we did that, we would just use our equation. And if we looked at the box we had before, we had a mass of 1 kilogram. We're going to multiply it by acceleration, which is 9.81 meters per second squared. And that will give us our force of gravity. Okay, again, force of gravity. And that would just be 9.81 newtons. So they're two different things. So if we look at this example now here, we can see we have our 1 kilogram box like we had before. And if we remember right, that box with a mass of 1 kilogram has a force or a weight equal to 9.81 newtons. And we could do the same thing with our 10 kilogram mass. We use our equation again, F equals ma. We multiply 10 kilograms, the mass, by the acceleration of gravity. And when we do that, we get 98.1 newtons. So weight and mass are connected, but they are not the same thing. What makes this specifically confusing sometimes is English, and specifically even American English. And it doesn't help the situation. Okay, so in Taiwan, like in most other countries, we use the English word weight when we're describing our mass in kilograms. So if I asked you how much you weighed, you would give me an answer in kilograms. Okay? So our everyday use of the word is incorrect, and that is where we get confused. You can't rely on what you just think or feel is the truth because of how we use it. You've got to remember the definition. Okay. So the thing is, though, in the U.S., they do use the right word because they don't use the metric system, and when you ask somebody from the U.S. about their weight, okay, they will give you an answer in pounds. And the unit of pounds actually is a weight. It is a force, and it's not mass. So in the U.S., you ask somebody how much they weigh, and they will give you an answer in pounds, which is indeed a force. So that is correct. But if you go to any other English-speaking country, or you go to Taiwan or somewhere else where they use English as a second language, and you ask them how much they weigh, they'll give you an answer in kilograms, right? But that's not technically correct because that is a unit of mass. So we may use the same word in daily conversation, but the answer we give depends on where we're from, not on the scientific definition of the word. So I'm going to give you one more example now of weight versus mass to really just solidify the difference in. So what we're going to do is we're going to look at our 1 kilogram box and our 10 kilogram box again. Okay, so we have them here, our 1 kilogram and 10 kilogram. And now just to make things a little simpler, I'm going to round our acceleration due to gravity to 10 meters per second squared. And we still have our equation. So on Earth, we already know, okay, that our 1 kilogram mass weighs 9.8 newtons, and we're now going to round that to 10 newtons. And we know that our 10 kilogram mass weighed 98 newtons, so we're going to round that to 100 newtons using our new acceleration here to make things simpler. So now it turns out that on the moon has 1/6 of Earth's gravity. So what that means is we can take our 1 kilogram box, and because 1 kilogram is mass, the mass stays the same. But now on the moon, that mass is going to have a different gravitational force because the acceleration due to gravity there is different. And that acceleration due to gravity is 1/6 of what it is on the Earth. So we take our 10 meters per second squared and we divide it by 6. And that gives us a value of an acceleration of 1.67 meters per second squared. So that's what we'll use to find our force of gravity on the moon. So we use our force equation. We have force equals ma. I'm not going to write it again. We'll plug it in. We have our mass of 1 kilogram times our acceleration of 1.67 meters per second squared. And that comes out to 1.67 newtons. We can do the same thing now with our 10 kilogram mass. Okay, and if we use 10 instead of 1 kilogram, then we'll end up with 16.7 newtons, which is not anywhere near the 100 newtons that it weighs on Earth. So weight depends on the force of gravity. Mass does not. That is their essential difference. So know this. You need to know that mass and weight are not the same thing. Okay? Not. Do not forget this. Know it. I cannot say this enough. So, now we are going to move on to our next topic, and that is normal forces. So, looking at this, a normal force is a force that acts on a surface perpendicular to that surface. And just a little vocab hint here, okay? In math and science, the word normal actually means perpendicular. So that's where that comes from. That's why it's a normal force, is because that's what it means. So we're going to look then about how the normal force's magnitude depends on the force of gravity on an object. So an example here. So here I have two objects. One is sitting on this sloped surface, and one is just sitting on a flat surface. Now, we've already been practicing free body diagrams, and I know that you know that whenever something is sitting on a surface, right, that surface ends up pushing it back to create a balanced force, so it's in equilibrium, okay, and that we've been naming it the force of whatever that is, but all of these are just normal forces, okay, so we could write F normal, or you can just write F N. And that is really the force of the table or the floor or whatever this surface is that the box is sitting on. Now, what we haven't gone over yet is what happens when we have this situation where we have a curved surface. Because our tendency is to just want to put that velocity vector exactly opposite of gravity. But that's not the case, okay? Because normal forces are always perpendicular to the surface because it's the surface that is providing that force. And so our normal force will actually be in this direction. Okay, so that if you kept drawing the line, you would see that it is perpendicular with the surface. And that would be our normal force. So now you might be wondering, well then, how does it keep it from moving? And we're going to talk about friction in a minute. But this is why things slide down, is when you have a slanted surface like this, your normal force does not directly count out your force of gravity. And so sometimes the force of gravity then is stronger than the normal force. And then your object will slide down. Also, your normal force is multiplied by this angle. And we're not going to do the math, but that determines the magnitude of this vector. So here we end up multiplying it by the cosine of the angle, and that gives us 1, so they're equal. Here, if we did that, we'd get a value less than 1, meaning that the force of gravity and the normal force component opposite are not balanced. So let's look at friction now, because friction is the other reason that your block might stay on that surface. So when we talk about friction, most of the time we mean the force of friction. So let's look at the force of friction. Friction is caused by the unevenness of a surface and acts in the opposite direction of motion. So here we just have a simple picture. If the block is moving this way, notice this is a vector but not a force. This is just the direction it's moving. Friction, and this time it is the force vector, is going in the opposite direction. So let's take a little closer at what the unevenness of a surface means. So here I have an example, okay, and say you're running on the road, and if we took a really close look at that place where your shoe is hitting the road, even though the road might seem smooth, or maybe it doesn't depending on the road, but even the parts that look smooth to the eye, if you looked at them in a microscope, actually have all these little bumps just like this, and so do the smooth parts of your shoe. And this might actually even be a better example because there's high points and low points and it's not uniform. So all these little bumps are what cause friction because at the molecular level it's not smooth. So they rub against each other, and if a little hill here gets stuck up against this hill, it's going to provide a tiny force that keeps it from moving forward. So that is the source of friction. Now, when we take friction a step further, we talk about static friction, okay, which is the friction between two objects that aren't moving, and kinetic friction, which is the friction between two objects that are moving. So here we have two cases, not moving and moving. And if you look at the definition of the word static and kinetic, here a little vocab hint, static means to be not moving, and kinetic means to be moving. So that's why these two types of friction are named what they are. Looking at this here now, I've got some pictures, and we're going to draw some vectors on this to help us understand what's happening. So in this static example, we have this person pushing on the box. So there's the force of our pushing. But depending on how big that friction force is, okay, it might not be enough to overcome it, okay? Our force of pushing might be less than the force of friction. And so the net force is still 0, okay? And I want to point this out here, actually. With the force of friction and static friction, that friction will always just equal the force of pushing. So we need to change this sign to equals. Let's use a different color so it's more clear. Okay, so the force of pushing is equal to the force of friction. And that is what keeps it from moving even though you're pushing on something. But eventually, if you push hard enough, or if you push strongly enough, or maybe you get a friend to help you, then suddenly your pushing force might get really big. Okay? I'm going to draw a big, thick arrow to help us remember that. So now our force of pushing becomes greater than our force of friction. And our force of friction is still going the other way, but it is smaller. And at that point, you have a net force here. Your net force is greater than 0. Okay? It's greater than 0, which means that it is now moving. So we are in motion. And once we are in motion, because it's easier to push things that are already being moved, the force of friction is actually slightly different than it is when it's static. And that's why we talk about static and kinetic friction, is because they'll actually be different values depending on those two things. The last thing we're going to talk about now is air resistance. So air resistance is really just a type of friction. And in class, we've already looked at what happens if you take a book and you drop it, and you take a piece of paper and you drop it. And we know that the paper will just kind of float down, whereas the book just drops straight. And we know that the paper floats down because of air resistance. But what air resistance is actually a collision or the hitting of the particles of the air and the object moving through the air. That's why all the particles of air can affect the piece of paper. The piece of paper is so light that those little forces add up. Whereas with the book, the force of gravity is so strong on it and it's so solid that even though those particles are hitting it, it doesn't really change its motion that much. But what air resistance does is it does slow down anything moving through the air. And this acts like friction, okay? And it acts in the opposite direction of motion. So let's look at some examples. So here's my example. We've got a ball here that's falling through the air with air resistance, and a ball that's falling through the air with no resistance. So if we drew free body diagrams on both of these, okay, both of these are on Earth. So we're going to have the force of gravity acting down on both of these. And in the area with air resistance, okay, the force of gravity is pulling the ball down. In this case, the ball is moving down. And so the force of the air resistance will be up. And most of the time, the air resistance force is going to be less than the force of gravity. But when there's no air resistance, we won't get that resistive force. And so we don't have to add anything new to our free body diagram. Now, what is different is if we take our ball and now we throw it up in the air, okay, so that the ball is moving up. In both of these cases that we've drawn here, okay, the motion of our ball is down. Okay, so that's the direction of motion. So if instead I took a new situation here and we threw the ball up, so that is the motion, okay, then we'll actually have air resistance pushing opposite the direction of motion. Okay, so that would be our force of air resistance. And gravity might be pulling it the same way. Okay, so air resistance, the direction of that depends just on the direction of motion of our object. And actually, with skydiving and things like that where you're falling out of the air, eventually you hit something called terminal velocity. And terminal velocity is just when your force of air resistance has gotten so big that it equals the force of gravity. And so the forces are balanced. And you're now in equilibrium while you are falling. So that ends section 4.4. Going a little bit more in depth to these forces that we've already been seeing. So please, again, let me know if you have any questions in class, or you can put them in Schoology, and I'll see you guys soon.